Swayam Prabha. Digital India. Educated India.
So, this problem of robot motion planning is as follows. So, I will quickly brush up on this. So, here is a change, no. So, the earlier one record as separate, from here you, and this would be like 5-10 minutes, like sort of just okay. So, here is your problem. You have a domain and you have polygonal obstacles, right. To make our life simpler, let us think of even convex polygonal obstacles. Okay. You can, the same thing can be argued for non convex thing, and say you have a point robot which starts from a source S and wants to go to a destination T. How do you figure out whether there exists such a path? You know of a data structure that can help you. These are obstacles. Yes. Polygonal obstacles. So, it can translate. It is a point robot, no, any motion. You can even talk of curves. So, you know of trapezoidal decomposition, no. So, do a trapezoidal decomposition on this set. So, consider them as separate line segments and do it, and for all line segments that are for all. So, if you do the trapezoidal decomposition, it will so happen that there would be even line segments inside, no. So, but forget about those inside line segments and just consider the outer one. So, now what you do is, can you now find a path through this? Now, see, if there exists a path, what you do is, per trapezoid, these are, mind you, trapezoids are convex bodies. So, any point is visible from anywhere, no. Okay. So, what you do is, put vertices for each trapezoid, and if two trapezoids are sharing an edge, so you can walk from the other one to the other using this doubly connected edge list. So, what you do is start. So, first locate in which trapezoid your robot is, then use an edge to move there. And mind you, even if your path is kind of a curvilinear path, there should exist a straight line path also, no. So, you can go somewhere and then it needs a proof, but let us now not bother about this proof. So, the point is, on this planar decomposition of trapezoids, you can, by assigning vertices to each trapezoid, you can move from one to the other, and you can form this graph, and on this graph you can sort of do a what your favorite BFS to reach there, no.
What guarantees that the path is successful?
Have I claimed so, sir? I have not as yet. Okay. So, that means, if there exists a path, you can surely figure that out. Again, this needs a formal proof, but you can at least get the idea of it. Now, yeah, what I am saying is, my claim is, if there exists at least a path, even a curvilinear path, I can figure that out.
So, you are not restricting any condition selection of the points inside the trapezoid.
No. So, what I am saying is, if there is a path through this free space, so what you do is, say let your box be R, and then you take the union of all polygonal obstacles. Call this, so this is your box R, each one of your these are your polygonal obstacles. Okay. Look at this set, and this is your free space in which the robot can move, and this is your forbidden space. Okay. So, my claim is, I have to do a proof which would take time, is if there exists a path in this free space, then via this trapezoidal decomposition I can find one for you. Fine. What I would possibly do is, if you are even more intent, what I would do is per edge of the trapezoidal decomposition I will keep one vertex. I was not that detailed earlier. If I take one vertex on a trapezoidal boundary, vertical boundary, then as a trapezoid is a convex piece, then there should always exist a non obstructing path like this. Agreed? So, you form your graph this way. So, when you move, when you are thinking of moving from a face to a face, go to the vertex of the trapezoid, jump to its corresponding vertex corresponding to that edge, from there you can jump there. So, there always is going to exist such a path, no? So, if there always exists a path in this free space, then you can also track it using this one, fine. Okay. It is a kind of an if and only if thing. Other point? What? So, S is the source, T is the destination. So, the point robot wants to go from S to T. What? Oh, so the way my graph is formed is, part trapezoid I take a green point inside, and on its vertical and these two bounding vertical lines I take another vertex. Okay. How is the graph formed? I join this with this, this with this, this with this, fine. This is the way the graph is formed. Now, if you have a path in the free space, it is surely moving through this trapezoidal decomposition, right. Apply induction, say you are at some vertex here. Can I go to the next trapezoid in this path? Surely I can, because I can go to an edge, go to a vertex on this edge, convex piece, I can go there, and from here I can go there. Agreed? So, that you can even write this proof in a more formal way. Okay. Now about the shortest path. You might not be happy with kind of a very long path, no? The first question is the shortest path going to consist only of straight line edges, or they can even have curves? First, right, you can write a proof of it, because if in this free space, think of this free space and think of any curvilinear path. So, if you have a curvilinear path in the free space, then you can have a small point, topologically speaking, there should exist a small ball in this free space, and then you can sort of short circuit this with a line, fine. So, there should exist no curves in your shortest path, right, first. Second, can this curve, can this, so now you know that your shortest path will have polylines, right. Can this dangle in the free space? One can show that this shortest path has to go through the vertices of these polygonal obstacles, because again one can give a formal proof. So, think of, I mean say you are bypassing this, no, say you are bypassing this. So, you have to bypass, we have already shown that you have to bypass with a straight line, then obviously these are convex pieces. So, then this would be obviously shortened, no. So, one can even show, again this needs a formal proof, but one can show that this. So, I have already argued that there would be straight line edges and they have to go through vertices of these obstacles. So, that tells you that you form the visibility graph of these polygonal obstacles. So, say for example, if you have a polygonal obstacle like this, then this vertex is not visible to this, because of this polygonal obstacle, this vertex is not visible to this one. So, what you do is form the visibility edges. Now, one can the idea is you can, if you are, I mean you can look at, say, so what can be a trivial algorithm? Look at all pairs of edges, look at all pairs of edges induced by the vertices of the polygon, no, intersect with all the existing other lines of the polygonal edges. If they intersect, those 2 points are not visible, right. So, consider all pairs of polygonal vertices, intersect it with the other n minus 1 lines or n lines to figure out the visibility. So, trivially you can do it in order n cube, done. One can bring this down to this, even one can bring it down to. So, this is kind of an output sensitive algorithm where k is the number of visibility edges, n is the number of all the number of polygonal vertices. So, that means if you now form the visibility graph is exactly in the free space, no, it is not in the forbidden space. So, if you want to form this, answer the shortest path question, what you do is form this visibility graph, taking that amount of time and those many edges, and then run a shortest path algorithm on this visibility graph. Things start getting interesting if this robot, instead of being a point robot, is a polygonal robot. Things would even start getting interesting if instead of this being convex, they are non-convex. Things would even start getting more interesting if this robot can, instead of only translating, can even rotate, no. So, you can bring in all sort of complications. So, and this is a fascinating area of robot motion planning, 400%, no. Okay, this is what I explained to you, no? This is what I explained to you. Now, think of this. Okay. First, figure this out that, say, this P, this capital P is the obstacle, okay, and this capital R is the robot. Now, what happens is, as because this robot has a volume, has a size, the entire size cannot intersect with the polygonal obstacle, no, the entire thing has to stay outside. Now, think of this, let me start by having a, can I just minimize this? Yes. So, think of the very simple case, say your polygonal obstacle is a rectangle and your robot is a circle which can translate. The question is, what is the forbidden space around this? I mean, what I am going to do is I am kind of going to play a relative velocity kind of game, no. When you have two persons moving with different velocities, what you do is get the velocity, I mean turn the velocity of 1 to 0, so that, right. I will do something like this in here. I will try to make this polygonal robot to a point robot by transferring its shape to the obstacle, so that I will grow the obstacles a little bit, right. So, instead of what their size was, I will have a forbidden space which will be a function of this red thing and this thing. Okay. Now, what does that say? That what you have to do is take this circle and sort of move it around, no? Okay. How should you move it around? Putting this, that is important. It is not like this, no? Then you are overestimating, right. You should rather take this point, sort of move this center around this and look at how this grows. So, essentially what will happen is, for the arcs you will have something like this at the corner, right, of a radius of, say, if the radius is r, you will have an r kind of arc here. This will look like this, this, no. And this thing in set theoretic terms is known as Minkowski sum, right. So, now see a point robot, if I now turn this red robot to this small point robot, it can, if it is not going into this zone, I am happy, because the moment it gets into this zone whose radius is r, then it will conflict with this polygon. So, this concept is known as Minkowski sum. Yes.
So, if that robot is translating, then at the corner it will make kind of
Circular arc.
Circular arc, but it will be the point, the center of the circle traces, it will be exactly the corner only, because it can't rotate, right. So, after coming to a point, it will not shift like this, but it will move.
It is a translation like this, no. Do it yourself, you will see. Okay. Think of this as your polygonal robot and this as your obstacle, no, and this is translating. So, see, this is always, if you look at it, this is always parallel to this, no, shape wise, and you have to figure this out. It is going to be very complicated. So, the way you do it is, you take a reflection of this around the center. Think of this, this is the forbidden zone, no. But to find, how do I find this forbidden zone? You know, translating it around, it is like, it is not a very good thing to do. But what I want to do is, I want to get this in a nice way. How I do it? You have to convince yourself that, you can write even a mathematical proof of it, that if you just flip the robot around this. So, what is this? That any x y point in this robot goes to, fine, that is it. So, now you have a new shape. Now, apply this Minkowski sum. How is it defined? So, you talk in terms of sets, right. Set is now this shape for you, you can think of them as vectors also. So, you take two vectors, one from this shape, one from this shape, do a vector addition, right, for all pairs. Now, one can show that this Cp is basically equals to this 2. You know, geometrically if you think it holds, but you can even write an algebraic proof of it.
The robot shapes will be convex.
Yes, I am dealing with convex shapes, I have not yet said that they are non-convex. Fine. Okay. So, the point is, you can find somehow the forbidden zone corresponding to a polygon. So, you have allowed the point robot to be a point and you have sort of suitably charged its mass around that polygon to make it grow such that. Now, we can go back to the forbidden space and think. Earlier, each one of your convex polygonal obstacles were non-intersecting, there was free space. Now, you have these robots and these polygonal obstacles have grown, they might intersect, and if they intersect, then it is like I have to maintain this complexity, I have to know what is what, how many vertices will be there, how many edges will be there, combinatorics back again. But one can show, and that is the interesting part of this study. No, how do I take this? Oh, the mouse can help me, no? Okay. So what I am sort of rushing through is, you can, by taking the help of Minkowski sum, that this definition, you can form this shape. The proof is there also in the book, no, fine. Now, forget about robots and think of something called pseudo disks. Pseudo disks are structures like this, so that circles can never intersect like this, no. Ellipse can, but circle cannot, no. So, it cannot sort of break through from one side and get out to the other side, right. So, you make this more precise by saying, you look at this set. So, this is this set, this would be connected, as well as if you look at these two sets should be connected. Then, so sort of what I am doing is, I am sort of generalizing circles or convex bodies to something more restrictive by saying that we will have pseudo disks. What I am going to show to you is, so earlier I had this convex polygonal obstacles which were disjoint, interior disjoint, no overlaps. I had this convex polygonal robot. I grew each one of them by this convex polygonal robot. Now they intersect, but their intersection pattern would not be arbitrary. If you take any two pairs from this intersection, they will be like these pseudo disks. And if they are pseudo disks, I can argue very well about their combinatorial complexity. So like the, I mean, this is not a pseudo disk, no, because this and this is disconnected. Similarly, this and this is disconnected. Okay. So, this theorem says, this is like, so given a set of convex objects with this right, this is nothing but your convex polygonal obstacles. Mind you, my initial thing was each polygonal obstacles are interior disjoint, fine. And what I did was, this was my convex polygonal robot. I grew each one of these T1, T2. I showed you that the way you grow it is by this Minkowski sum. So, now in the domain what I have is a point robot and these shapes. My claim is this shape is a set of pseudo disks. How do you prove it? The proof is not very difficult. Think of, so T1, T2 is disjoint, no? But think of a common upper envelope tangent, lower envelope tangent, and look at extremum points of T1, T2 in perpendicular directions of these two tangents, fine. So, this is set D2. Now, in this direction, so now if you start rotating this, so if you start rotating this, in these directions T1 will be extreme. These are convex shapes, disjoint interior. So, there you will have a continuous domain in which T1 would be extreme, then we switch over in which direction T2 would be extreme, fine. So, this is a property of convex polygons, disjoint interior. Now, what you have done? You have taken the Minkowski sum of these shapes with another convex polygon, which was your robot. Okay. Now, say they are not pseudo disks, fine. If they are not pseudo disks, then they should intersect something like this, right. So, there would be, you know, now you understand. So, what is your Minkowski sum? Say, so if you take say P 1 from T 1, a vector sum with R, right, R comes from the robot, and then you take a P 2 vector sum with R, no. So, whichever is extreme, so either P 1 would be extreme or P 2 would be extreme, right. So, that would push that to be the extreme. Now, if it is a pseudo disk, then it will so happen that in this direction P 1 would be extreme, then it will change to P 2, then it would change to P 3, again to P 1, then again to P 2, but that violates this condition, right. So, what happens is these shapes, these convex polygonal shapes which you have obtained as the Minkowski sum of interior disjoint convex polygons forms a pseudo disk, set of pseudo disks. And if they do and that is the proof that I said, and if they do then let us look at. So, now what has happened? There are many such pseudo disks which have intersected, no, and I want to figure out what is the complexity of, can I not change the colors? No, I wish more, no. Anyway, so I am interested in the complexity of this. How many such vertices will be there, how many such arcs will be there, how difficult a shape it is. Okay. To do it, I do as follows. This is kind of a charging argument. So, this union will have what kinds of vertices? Some vertices will come from the original polygon, right, and some vertices will come from the intersections. Vertices which come from the original polygon, charge them, right. So, there are two kinds of vertices, one which comes from the original polygons, the others which are formed because of this intersection of pseudo disks. So, these vertices are easy to count, there will be at most n many of them, no, forget about it. Look into the other ones. In the other ones, what can happen? So, this is this intersection that I have to count, E 1 is one edge, E 2 is another edge. What can happen is E 1 can go into cut E 2 and go into another pseudo disk, fine. It may finish within E 2 or go out of E 2. So, these are these two cases, fine, but mind you this case cannot happen, then it is not a pseudo disk, no. Okay. Now, if this case has happened, what you do is travel along E 1 and look at the vertex where it has ended, it is within a pseudo disk bounded by this edge E 2. So, charge this vertex, put a charge on this vertex. So, what has happened is you have transferred the charge of this vertex to this one, and mind you this was a vertex of your original polygons. How many such charge can one vertex have? It can have only two such charges, agreed? That was one way of counting. For the other, if E 1 budges through this shape E 2, which is again a pseudo disk, and goes outside, then it must be so that E 2 should finish inside, otherwise it would be a pseudo disk. Then put this charge here. So, what you are doing is essentially looking at all intersections and intelligently shifting the counting charge to the original vertices. So, there were n many original vertices to start with, and because of this shifting charging argument to close, I saw that you can shift only constant number of charges, no. So, in all you are going to have, what is your now count, order n. So, now it is, now you see what you have shown is right. So, there were shapes like this and there was a robot. So, what happened was each one grew up, but they were pseudo disks, right. But what I have argued to you is this, the number of such vertices and this complexity is linear. though they have now grown to intersect, but then it is still manageable linear. Again you apply your trapezoidal map, go ahead. In the union of these pseudo disks you cannot get into, that is the point. Okay. So, it was convex robots, convex disjoint obstacles. Now, if both are non-convex, what do? You triangulate. You know triangulation, no? You triangulate. So, now you have a bunch of triangulated robots, triangulated thing, it is convex, get that theory. The count will obviously increase, you cannot now expect, because now you will have order n many triangles, no. So, this is the essential theory. Now, essentially you see I did a counting, no, and if you look into this kind of pseudo disk properties, I mean, see remember this, there was a question in the tutorial which asked you to look at this Voronoi diagram beach line and asked you to figure out how many beach lines are there. Essentially these parabolas are kind of pseudo disks, they do not budge like this, no, the parallel, and this argument tells you that the number of would be order n. If you are intelligent with your counting, it will be 2 n minus 1, and this sort of things gives rise to many things. Think of this, you have n lines on the plane. Okay. What you do is you look at this minimizer function that Orijit talked of, right. Now, what will happen is if you have lines, so there will be situations when our minimum interval zone would be influenced by this line, right, then there will be another line, so then this line will go off. So, now if you look into the interval of this minimizer function, you will have intervals corresponding to some lines. The question is how many such intervals can there be on this line? Those of you who are interested might look at something called, I thought of getting into this, but so it is Davenport-Cinzel sequence. The interesting thing is if you have lines and you look at this lower envelope, so this part is minimum, and you look at the complexity of so this is like, if this is line L1, I say this is L1, then it is this L2, then maybe somewhere it is L3. So, you look at this sequence L1, L2, L3, no, and you try to argue how big is this sequence. It will dramatically change if instead of lines you have line segments. But if you have line segments, it might be so that you can have a sequence like this. Sometimes L1 is less, then it changes to L2, then it can again L1 can come in, no. So, it might change. So, if you look into now this sequence for line segments, this might even get to quadratic, right, and these sort of things are captured by this Davenport-Cinzel sequences. So, those of you who are interested might look at that. Okay, I think I would end here.